Hey everyone, my name is Evan Youngberg, and today I'll be sharing with you the research I did at NASA Langley Research Center during summer 2020. So this project was called Validation of an Automatic Segmentation Procedure for Kink Bands. This is where I was looking at an algorithm that automatically found kink band damage in a composite material. So what is a kink band? A kink band is a common failure mode for composite plies when subject to a longitudinal load. And you can see in a carbon fiber composite ply, you typically have fibers that are parallel and straight, but a kink band is when they're misaligned by some angle phi, as you can see in the figure. So the way this was created is we had a test specimen, as shown in the bottom right, and this was placed in a loading rig, as shown in the bottom left. And this loading rig applied a longitudinal load that damaged the material and created kink bands. And during this, it was scanned with an X-ray CT scanner, and it created these 3D image stacks. So here's what they look like. You can see that the cutting plane goes through the test specimen as shown, and then this creates images as shown on the right, and you can see in the middle of it that misalignment of fibers there, that is the kink band. And so we wanted to take an algorithm to automatically find these kink bands. The way this worked is it used Sobel edge detection to look for horizontal lines, and when it found a horizontal line, it marked it as the kink band, as you can see in those images. So what we could do with this is, as you can see on the left, there's 3D figures that can show the kink band, and we can see how it changes over time. And what I wanted to do with this data is I wanted to validate the algorithm that automatically found the kink band. So the way this was done is we had this data that was automatically found from the images, and then we also had manual data where somebody manually clicked on the kink band in each image, and we wanted to compare those two. And the way this was done is these 3D figures were projected onto a 2D plane as shown, and then a convex hull function was applied to trace around the area of the kink band and calculate the interior area. And then these two, for the automatic and manual procedures, were placed on top of each other as shown. So we have two kink bands here, and with one of them we have an 8.7% difference between the automatic and manual procedures, and the other one 12.1%. So what caused this difference in the area? To answer this question, we looked at the top and bottom of the kink bands and found that the automatic procedure could not identify the kink bands accurately in those areas. And here is the reason for that. The Sobel edge detection looks for horizontal lines in these images, and the problem is when you get towards the top and bottom of the image stack, you are getting images that include both 90-degree plies and 0-degree plies. This is called the ply interface area. And these 90-degree plies were showing up as horizontal lines and were being marked as the kink band. So you can see in frame 5, we get a lot of misidentification points, where in frame 25, it is correctly identifying it. So basically, we cannot use images at the top and bottom of the image stack. So those have to be trimmed off. And then I was wondering, how do the areas compare if we do not consider this known limitation in the automatic segmentation procedure? So looking at this, we can find that 70 to 75% of the difference in the two areas is caused by this ply interface error, and that the percent difference in area is pretty small when we take this out of consideration when calculating the percent difference. So another question we have to ask is, if we look at kink band 2, we can see that the automatic and manual data does not line up that well in some areas. So here is why. So at the bottom of the kink band, we can see that the automatic and manual data lines up pretty well, and if you look at the image, we can see that the automatic segmentation procedure is finding the kink band pretty well. But if we look at the top, as shown in the bottom right, we can see that it's missing a lot of areas of that kink band. And the problem is that the automatic segmentation procedure is having trouble identifying the really thin areas. So the way this is affected is by a sensitivity parameter. The sensitivity parameter determines how sensitive the Sobel edge detection is to finding horizontal lines. This has to be set on a case-by-case basis. So we can see that that middle image is doing a really good job finding the kink band, but making the sensitivity parameter a little too sensitive, as shown on the left, creates a lot of false positives, where on the right, it's missing some areas of the kink band. So this leads to some conclusions. There's a less than 5% difference between automatic and manual processes for kink band segmentation when we account for that known ply interface error. And these results show that the automatic segmentation procedure works really well in some cases, but the sensitivity parameter has a large effect on its accuracy. So in the future, the automatic segmentation procedure can be tweaked to optimize that sensitivity parameter and better detect thin parts of the kink band. And then this can be applied to automatically segment more kink bands and show how the kink bands change over time. Thank you for watching.